Good evening. My name is Gerard Beagle, and I'm president of Shannon & Wilson. On behalf of Shannon & Wilson and the University of Washington Civil and Environmental Engineering Department, I would like to welcome all of you to the 2017 Stanley D. Wilson Memorial Lecture. It's great to see so many people in attendance here. This year we celebrate our 63rd anniversary since the founding of our firm by Stan Wilson and Bill Shannon here in Seattle. Mr. Shannon was involved in many high-profile projects during his time at Shannon & Wilson, including an extensive investigation of the 1964 Alaska earthquake. He became the founding president of the Associated Soil and Foundation Engineers, now known as ASFE GBA, as well as a founding member of Terra Insurance, a group formed to provide professional liability insurance for the engineering community. We appreciate the contributions that Mr. Shannon made to our profession. Our other co-founder, Stan Wilson, has been characterized as the idea man. He was technically gifted and was respected for his extensive knowledge of earth and rock-filled dams and their instrumentation. He developed instruments to measure displacements and distortions in soil and rock, many of which are still used today. Stan served as a consultant on large projects all over the world. On one of his consulting trips, he contracted malaria, and in 1985, his career was sadly cut short by an untimely death from the complications of his illness. To honor Stan's legacy, our firm established the Wilson Lecture in 1989 to foster and maintain the spirit of thoughtful and practical engineering solutions. For this year's lecture, it's an honor and a privilege to have our own Dr. Stephen Kramer from the University of Washington deliver tonight's lecture. I'm sure that Professor Kramer doesn't need an introduction to this crowd, as he's taught many of you, and we all know him well. His name is synonymous with earthquake engineering and the University of Washington. He's a highly sought-after earthquake engineering expert throughout both the U.S. and the world. In the words of my now adult children, he is truly a rock star in this business. Dr. Kramer has been at the University of Washington since he received his PhD from UC Berkeley in 1985. His primary research interests include soil liquefaction, site response analysis, seismic slope stability, and hazard analysis. I had the pleasure of reviewing his impressive 32-page curriculum vitae. I counted over 120 publications, one book on geotechnical earthquake engineering that is used at almost every engineering university, and 4 major chapters in books on earthquake engineering. He's led over 50 sponsored research projects that totaled over $5 million for the university. He's consulted with almost every geotechnical engineering firm located in the Puget Sound area. We're extremely blessed to have him at the University of Washington. His list of awards is about as long as his list of publications. In 1988, he was a recipient of the Presidential Young Investigator Award from the National Science Foundation. In 1991, he was awarded the Arthur Casagrande Professional Development Award from ASCE. In 1996, he won the Walter Huber Research Prize from ASCE. In 1997, the John R. Kiley Professorship Award from the University of Washington. And in 2009, the Norman Research Medal from ASCE. Lastly, he was named the Puget Sound Academic Engineer of the Year by the Puget Sound Engineering Council in 2012. Without further delay, please help me welcome Professor Steve Kramer.
Well, thank you very much, Gerard. It's a pleasure and a real honor for me to be here this afternoon. I've come to almost all of the Wilson lectures since they were established, and I've enjoyed hearing from the the many distinguished guests that have presented this lecture in the past. I have a Shannon Wilson story, I guess. When I graduated with my master's degree back in 1979, I was in the Bay Area, a Berkeley graduate, and I was looking for a job. And it happened to be, job market fluctuates, and it happened to be a good time when I was interviewing. So I interviewed at 12 companies. I got 11 job offers. The company I didn't get a job offer from was Shannon and Wilson. And so the fact that I'm here giving the Wilson lecture means a lot to me. I think it's very good evidence that Shannon Wilson's standards have really dropped. In the early days of the Wilson lecture, the speakers were colleagues of Stan, Mr. Wilson, who had worked with him. And I believe it or not, I'm younger, and I never worked with him, but I did have the opportunity to meet him. And I'd like to take a minute to tell that story. When I was getting my master's degree, I was asked to TA a special summer course that the Berkeley faculty put on for the Army Corps of Engineers. It was a great opportunity. I got to sit through in 10 weeks, hear all of the master's lectures, and actually listen instead of trying to take notes. And every week they brought in a guest lecturer, and they were big name people: Ralph Peck, Lyman Reese, John Folk, John Schmertman, really big name people. And my job was to go to the airport, pick them up, and bring them to the Berkeley campus. Well, Stan Wilson was one of these, and out of all of them, some of them were nice, and some of them didn't give me the time of day. But Stan Wilson was by far the nicest guy. He really impressed me. He asked me what I was doing. He was interested in what I was doing, and I just really had a great feeling about him at that time. So I drove over to San Francisco Airport, brought him back, dropped him off with Professor Seed, and I went back to my apartment, and because there was nowhere to park a car near the Berkeley campus, dropped my car off, got on my motorcycle, rode my motorcycle back to hear his lecture, because motorcycles were easy to park. At the end, I had to go take him back to the airport, and so Professor Seed brought him to me, and I said, well, I've got my motorcycle here. I need to go get my car. And he said, well, I could ride on your motorcycle. And Professor Seed said, no, you're not doing that, which probably wouldn't have been a good idea anyway. And he said, well, how far away is your apartment? And I said, well, it's about a mile away. And it was about an 80-degree day, which was a nice day, a little cool for me back in the California standards. And I now realize after 33 years living in Seattle that 80 degrees is a scorching hot, unbearable temperature. But we set off walking, and I thought, this is great. This old guy, I was 22, and going back through his biography, and now I know he was 66. We're walking along, we're talking, having a good time, and we walked up to my apartment. I went in to get my car keys, and I came back, and there was a window next to the door, and I look out, and Stan Wilson is like slumped over my car. And I think, well, I could go get an MBA, I guess, because I'm never going to work in this profession again. I killed Stan Wilson, and I opened the door, and he kind of came back, jumped up. He was just resting a little bit, and I got him some water, and he was fine, and we continued on. But I thought my career was over for a while there. So at the time, he was 66. I thought he was very old. Now I'm 61, and I don't think he was that old anymore. If I look at this picture, he had more hair at 66 than I have at 61. But when I was 22, I had more. So let's go ahead. I'd like to talk about some of the work that we've been doing here over the last several years. And I'd like to acknowledge some of the support that I've received from the National Science Foundation and the Pacific Earthquake Engineering Research Center through the PEER Next Generation Liquefaction Project. And then some students and colleagues who have really contributed to this work. Mike Greenfield is here somewhere. A lot of what I'm going to talk about is Mike's work. Sam Sedaris is responsible for a lot of this as well. Pelin Ozner is a colleague from Istanbul who spent a sabbatical with us working on this. Katie DeLaviaga ran a bunch of tests. I'll show some of her results when she was at NGI, and a couple people from University of Texas also helped out with this. So I think most of the people in the audience are familiar with liquefaction. We've seen it in a lot of earthquakes. It started, our interest started in 1964 when we had earthquakes in Niigata, Japan, and in the Anchorage area of Alaska. And it caused a lot of damage that hadn't really been seen and documented very well prior to that. We've had since then many different earthquakes in California that produced liquefaction, in Kobe, Japan, in Turkey, and in Taiwan. And recently we've seen some large earthquakes in Chile and Tohoku. And these are really particularly notable for the very large magnitudes, 8.8 and 9.0. We know that we get a whole range of different sizes of earthquakes. Small ones occur fairly frequently, large ones more rarely, and the really big ones luckily don't happen very often. If we look at earthquakes of magnitude greater than 8.5, here's a USGS list. 6 of these have occurred in the last 13 years. If we look at a plot of how these big earthquakes have occurred, kind of had a gap between 1964 and about 2003, but we've had a whole bunch of them recently, not in this area, but we've seen the kind of damage that they can cause. So in Sumatra, enormous tsunami caused tremendous damage in Indonesia, Thailand, Sri Lanka. The Male earthquake caused a lot of damage, including liquefaction along the coastline of Chile. And then, of course, the Tohoku earthquake that occurred 6 years ago in Japan. And then, again, a big tsunami, but a lot of other damage as well. We're concerned about this because we live near the Cascadia subduction zone off the coast of Washington, and it's also capable of producing these kinds of very large earthquakes. The big earthquakes come from subduction zones. This thing stretches from Vancouver Island down to Northern California, about 1,100 kilometers long. The width we don't know quite as well, but we know the basic mechanism that's occurring. And the Cascadia subduction zone produces 2 different types of earthquakes. What we call intraplate earthquakes, where the subducting slab kind of breaks as it dips down below the continental crust. And that produces the kind of earthquakes we've seen in this area over the last 60 years or so. So the 1949 Olympia earthquake, the 65 SeaTac earthquake, and the Nisqually earthquake were all of this type. But what we're very concerned about is the interplate earthquake that occurs on the rupture, on the contact between the subducting Juan de Fuca slab and the North American plate. And that's what's capable of producing these very large earthquakes. And we know from tsunami data in Japan that the last one was January 26th of the year 1700. There are a lot of estimates of how this kind of earthquake might occur. There are a series of segments of the Cascadia subduction zone, and each of them could rupture in various combinations. We would have different lengths and would release different amounts of energy, so there would be different magnitudes associated with them. These ruptures usually occur at about 2.5 kilometers per second, and so the time that it would take for 320 kilometers to unzip would be about 2 minutes or so, and it would go all the way up to 6 minutes for the entire fault Cascadia subduction zone to rupture. That doesn't mean that the ground would be shaking in any one location that long. If we're up here in the Seattle area, we're not going to feel the rupture down here. It's too far away, but we will feel some long duration motions. We can do some simulations of these kinds of events. So Art Frankel of the USGS, who's here on campus, has done some of these types of things. Here's one scenario where we have 2 asperities, strong spots that can release a lot of energy when they rupture. And in this simulation, we can see we're getting peak accelerations about 0.2 to 0.3 G or so. Strong shaking, but not exceptionally strong shaking. The duration, though, would be on the order for us here about a minute or so, a little lower, a little higher, but a couple minutes up down in the Portland area. Another scenario would involve 3 asperities. And in this case, we have the energies distributed out a little better, a little bit lower level of ground shaking, but we're looking at 2 to 2.5 minutes or so of shaking here in the Seattle area. So when we look at earthquake ground motions, they're affected by the magnitude of an earthquake. Here we have 6 ground motions all plotted to the same scale for different magnitudes. So the magnitude is increasing as we go down. We can see that the amplitude of the ground motion is increasing. We can see that these larger magnitude earthquakes produce more low frequency energy, so the predominant period increases. And we can see that the duration of shaking increases as the magnitude increases. So these very large magnitude earthquakes produce ground motions that shake the ground for a very long time. When we look at ground motion characteristics, we usually characterize amplitude and frequency content in kind of an approximate way by means of response spectra. And we often take the response spectra to be our definition of the earthquake. But we know, I think a lot of people in this room, some might remember, amplitude, frequency content, and duration are important. We define duration in different ways. We can define a bracketed duration as the time between the first and last exceedances of some threshold, or we can define a significant duration by integrating the square of acceleration over time and taking points at 5% and 95% of that ultimate value, or 5 and 75% of that ultimate value, and use those as measures of the duration of a ground motion. We have ground motion prediction equations that can predict what the duration will be as a function of earthquake magnitude, but most of them are based on data that are limited to magnitudes less than about 8 or so. They're pretty consistent up to magnitude 7 or 7.5, but then they start to diverge, and if we take the liberty of extrapolating them, we see that we don't have a very good ability to predict what the duration of a magnitude 9 earthquake is going to be. So there's a lot of uncertainty in that. We can look at ways of describing the ground motion that are influenced by duration. Response spectra are what we normally use to describe ground motions. We wanted to see the extent to which response spectra helped us understand duration. So Sam Sedaris developed a series of band-limited white noise motions. We took white noise, filtered it in the frequency domain by a Brun spectrum so that it had a frequency content that's representative of earthquakes, and then applied some time domain envelope functions so we could create a bunch of ground motions that had the same amplitude, same frequency content, but different durations. And we looked at what effect they would have, say, on response spectra. And so if we take some relatively short duration motions, the time that's listed in the upper right is really the length of the record rather than a measure of the duration. 2 seconds, 4 seconds, 10 seconds, and 20 seconds, the response spectra is affected by those durations. And so we can see that for very short durations, the spectral acceleration increases, so it's sensitive to the duration of the motion. When we go to longer duration motions, now 50, 100, 200, and 300 seconds, the spectra are all about the same. And so for longer duration motions, the response spectrum isn't influenced by duration. And so a response spectrum by itself is not enough to tell us everything we need to know about the characteristics of a ground motion. So we can then go to things like evolutionary intensity measures that change with time. So here's a time history. We can calculate a magnitude-corrected peak acceleration by dividing the peak acceleration by a magnitude scaling factor. So over the course of an earthquake, the peak acceleration is going to increase in a series of steps. And we can count the number of cycles, calculate a magnitude scaling factor from that, divide the PGA by a magnitude scaling factor, and we now have an evolutionary version of the magnitude-corrected peak acceleration. This is the parameter that we currently use to characterize loading for liquefaction problems. So when you calculate a factor of safety for the triggering of liquefaction, you're using this parameter, but you're just using the final value. And so here we're looking at how that evolves over time. It increases in a series of steps as the PGA increases, and we can see that it is sensitive to the high frequency components of the motion. It jumps up when we have some high frequency components here. If we look at something like Arias intensity, where we're integrating acceleration squared, it increases but more smoothly, and it's not affected so much by the high frequency parts of the motion. Cumulative absolute velocity, the integral of the absolute value of acceleration, is even smoother, and it's more sensitive to the low frequency components of the ground motion. This motion is from the wildlife site in Southern California. Thanks. Liquefaction occurred there at about 13 seconds, indicated by the vertical line here. If we look at our different intensity measures, PGA sub m, most of it builds up before liquefaction has been triggered. So we can break it into a pre-triggering and a post-triggering component. And the post-triggering component is very small, so it's not really telling us much about what's going on after liquefaction's been triggered. It tells us more about what's going on before triggering. For Arias intensity, we're seeing a lot more sensitivity to the the part of the loading that occurs while the soil is liquefied. And for CAV, it's even more so in that direction. So we know that liquefaction is caused by the generation of pore pressures. During earthquake shaking, we have tests that we can perform in the laboratory to try to measure this kind of behavior. From the very earliest days, this is one of the first cyclic triaxial tests ever performed. It's kind of a step loading function, but it still shows us some important things about liquefaction. Here's the loading, here's the strain or the deformation of the sample, and here's the pore pressure generation. And so as the cycles of loading are applied, we see an increase, a steady increase in the pore water pressure. Eventually, liquefaction occurs when the pore pressure gets high enough, and we see that before liquefaction was triggered, our strains, a measure of deformation, is very small. After liquefaction is triggered, all of a sudden they become very large. The soil sample became much softer. Normally now we perform these types of tests using harmonic loading, a sinusoidal loading, and we see the pore pressure builds up with kind of a characteristic pattern. It starts out with a rapid rate of buildup, then it slows down, and then it gets fast again. If we look at stress strain curves and stress paths, which we commonly do when we're looking at this kind of laboratory data, in the first cycle of loading, we see a little bit of pore pressure build up, so the effective stress decreases. The stiffness of our soil, though, is quite high here. As we have more cycles of loading being applied, the effective stress goes down, the soil becomes softer, and we start to see our effective stress path going in this kind of a butterfly shape. The effective stresses can become very, very low, but then the soil dilates and the effective stress increases as it dilates. And then we get a reversal and the effective stress becomes low again, and then we get dilation in the other direction. That change in effective stress causes a stiffness of the soil to change because we know those two things are related. So when the effective stress is very low, the stiffness of the soil is very low, but then it dilates. And so we start with a low stiffness, and as the soil strains, it dilates, the effective stress goes up, and it becomes stiffer and stiffer. Then we have a reversal. It's momentarily stiff, but then it quickly softens, and it goes back and softens and stiffens in the other direction. So it's really a very complicated form of loading. It has implications for the site response that we see in the field. Here's a profile, 10 meters of saturated sand over clay as a result of a numerical analysis. And it shows the colors represent the amplitude of the acceleration. Here's the input motion. This is a motion up at the ground surface. We can see as this motion comes up through the clay, we can see kind of a broad, diffuse band of acceleration as it travels upward. When one of these pulses hits the interface between the clay and the sand starts to liquefy. It becomes much softer. And so the first part of a pulse that hits this interface is hitting a soft soil, and it travels upward fairly slowly. The next part of that pulse comes in a little later, but the soil will have dilated at that point, so it's a little bit stiffer. And so the later part of that pulse travels upward a little bit faster. And the next pulse comes in later yet, but it's traveling up faster because the soil is becoming stiffer and stiffer. And what we see is this kind of diffuse band of energy here, or this one. They become more focused as they go up to the ground surface. And so we see these pulses of acceleration that have occurred after the soil's been liquefied. So there's a common conception that once the soil's liquefied, it's really soft and it stays soft, but that may not be the case. We see this to various degrees in different records. Here's the Kawagishicho. This is the apartment buildings that are famous for having tipped over that I showed earlier. It's very loose soil. There aren't any dilation pulses, any significant dilation pulses here. But here's Kushiro Port, where liquefaction occurred, and the soil was pretty stiff, pretty dense, even though it liquefied. And there's a lot of prominent dilation pulses here. You can see the peak acceleration for the whole motion is controlled by a pulse that occurred after liquefaction had been triggered. Wildlife, same sort of thing, a lot of dilation pulses. So we're seeing very soft behavior out here with these intermittent episodes of stiffness. Well, when we look at actual ground motions, they have a very different character than the kind of sinusoidal motions that we assume in the laboratory. And so we see that pore pressures build up in a different pattern. So we get a jump in pore pressure, then not much, another jump. And we see that things are a lot more complicated when we start looking at reality. When we look in the laboratory, when we perform this kind of transient loading test, here we can see our pore pressures are building up, but pore pressure really jumps and the effective stress drops quickly in a couple of main cycles there. We see evidence of dilation as the effective stress becomes very low, but then it dilates up and stiffens again. And we see the result of that in the stiffening that occurs in our stress strain behavior. The total amount of pore pressure that we get depends on the amplitude of the loading and on how many cycles we apply. So we can get loading liquefaction occurring from a strong input motion or a strong high stress level in just a few cycles, or with a lower level of shaking, we can still get liquefaction in a long number of cycles. So it's an incremental buildup of ratcheting upward of the pore water pressure. If we have test soils of different densities, the higher the density, the more resistant we are to liquefaction, as we all know. The slopes of these curves give us an indication of how sensitive the soil is to the duration of a ground motion or to the number of loading cycles that are applied. So we have laboratory test results, and then we have real loading, or we have laboratory loading and real loading, and they look different, and so we try to relate them to each other by calculating a uniform series of harmonic stress cycles that are equivalent to the transient loading history. And there's a whole bunch of ways of doing that, of counting cycles, but our cycle counting procedures, the ones at least that we most commonly use, don't pay any attention to the order in which these cycles are applied to the soil. So we could take a time history of loading that looks like this. We could rearrange those pulses from strongest to lowest or from weakest to strongest, and they would all be considered to be equivalent by our conventional procedures. If we looked at two cycles with the same amplitude, we would assume that they had the same potential for generating pore water pressure in our soil. We know that this number of equivalent cycles increases with increasing magnitude. To a lesser degree, it changes with distance, but it's not a very, very strong effect. If we start looking at how liquefiable soils actually behave when we have loading that's not just constant amplitude harmonic loading, we ran a test in a cyclic torsional shear apparatus that applied a loading that looked like this. So the loading increased and then it decreased. The increasing and decreasing portions were the same. If we look at two cycles that have the same amplitude, we can compare their results. The pore pressure that was generated in this loading sequence looked like this. If we look at the rate at which pore pressures were generated, more than 80% of the pore pressure was generated in the first half of the loading and only 20% in the second half. So the effect of the loads when the pore pressures were increasing, when the loading amplitude was increasing, was much greater than when it was decreasing. If we look at these two cycles that had the same amplitude, we can see a lot more pore pressure was generated, a much bigger increment of pore pressure was generated here than was generated out there. So a given pulse of stress will produce more pore pressure when it hasn't been preceded by a bigger pulse in the past. Conversely, a pulse that has been preceded by a larger pulse doesn't tend to produce as much pore pressure. So the order of these loading cycles affects the pore pressure generation. The timing of the pulses is important. So time is important from the standpoint of durations. Time is important from the standpoint of initiation as well. Looking at another test where we performed transient loading, we can see we had some weak loading initially. It didn't generate any pore pressure. Then we had a couple cycles of strong loading that generated a lot of pore pressure. And then we had some loading that was still pretty strong, but it barely did anything to the pore pressure. And so these cycles are in a sense shielded by these earlier cycles that had a higher amplitude. So the order of the cycles matters, the timing matters. Here's one more test. This was run at NGI this last summer. In this case, we have a cyclic simple shear test with transient loading being applied to a sample that has a static stress being applied to it initially, a constant static stress. And so there's the loading history. Here's the pore pressure that was generated. And this is the strain that developed. And we can see that since we had a static shear stress being applied, we developed a permanent strain in this element. So we're essentially modeling here a sloping ground condition, and we end up with a sample that has a permanent distortion to it. Then we took the same sample, after noting that here's when liquefaction occurred, we can see that before liquefaction occurred, our strains are very small. After liquefaction occurred, they're large, and they include this permanent component. We took that motion then and we reversed it in time. So the same motion, but we just ran it backwards through the sample. So by all our cycle counting methods and all our procedures, we would assume these two loadings to be equivalent to each other. Here's the generation of pore pressure. So the pore pressure generated more slowly, but it reached a high level also. And here's the strains that were developed in the soil. And so we can see for the forward case, our initial case, we had 8% shear strain. That's quite a relatively large amount of shear strain, and only 1% for the other case. So the order of these cycles matters for pore pressure generation and for the development of permanent deformations. So this could be the deformations of an embankment, a dam, a slope. This sort of thing turns out to matter when we look at our ground motions more carefully. What we do typically to account for duration is to use a magnitude scaling factor. And we usually calculate these things from the slopes of curves like this that come from the laboratory. And what it effectively does is increases the loading for larger magnitude earthquakes. And so we have our magnitude scaling factors. A number of people have proposed different magnitude scaling factors, and these are what we use in our conventional practice. If we look at effects on site response, our stiffness is a function of the effective stress. It's proportional to the square root of effective stress, essentially. We can write this in terms of our initial effective stress and a pore pressure ratio. We can then look at the characteristic site period for a simple site and substitute these relationships in, take advantage of our knowledge of the relationship between the stiffness and the shear wave velocity, and show that our characteristic site period, the fundamental period of our soil deposit, varies with proportional 1 minus the pore pressure ratio raised to the negative 0.25 power. If we plot the ratio by which the site period increases or the natural frequency decreases, we can see that it doesn't change all that much up to relatively high pore pressure ratio. So if we're at an 80% pore pressure ratio, that's not that big a change. But when we get to start approaching liquefaction with a pore pressure ratio of 1, these characteristics, the frequency characteristics change very quickly. And the ability of a soft soil deposit to transmit high frequencies up to the surface diminishes. And we see that in our ground motion records. We can look at things more carefully using time frequency analyses. And so we're plotting here what's called a Stockwell spectrum. It's kind of a combination of Fourier and wavelet-based procedures, normalized for amplitude. For the Kawagishi-Cho motion, we can look at this visually and say, okay, we got a lot of high frequencies here, things are changing quickly, and then we have low frequencies after that. We can decompose that in a plot that shows us how the frequency content is changing over time here. And we can see very easily that at about 13 seconds or so in this record, 10 seconds or so, the high frequencies drop out and the low frequencies become more prominent. So that's what happens when the soil liquefies. Here's another case. It's not as obvious to look at it visually. This is a Ibaraki 14 instrument that was in a Tohoku earthquake. And we can see again, looking at it this way, we've got a lot of high frequencies up to about 106 seconds, I think. And then those high frequencies dropped out and the low frequencies become more amplified. So we can start to look at the timing of liquefaction through these kinds of analyses. So Sam and Mike Greenfield and Pei Lin all have worked on this. Mike's really refined our procedures to be able to do these kinds of analyses and gather this kind of information. From the standpoint of lateral spreading, one of the primary effects of liquefaction, we know that we usually use empirical procedures to do this. Some people use sliding block analyses. They are correlated to peak accelerations. There aren't any case histories really at all, field case histories, where we have good ground motion recordings in the vicinity of a lateral spread. And so we're forced to use proxies for duration. And most commonly, we account for that by looking at the magnitude of the earthquake that caused the lateral spread to occur. And so if we look at a typical site and use a number of different procedures, a couple empirical and a couple sliding block-based analyses, we see that certainly our deformations increase as the magnitude of the earthquake increases, but there is a lot of variability there. And our uncertainties and predictions of lateral spreading displacements is really quite high. So we have this high uncertainty to deal with. When we look at the very long duration earthquakes, they are significant in a number of ways. We could expect, because of the long duration, the large number of cycles of loading that are applied, we can get liquefaction occurring at greater distances. There's a whole bunch of combinations of magnitude and peak acceleration that can trigger liquefaction. If we look at a material with 15 blow counts, we can trigger liquefaction, say, in a 0.28 G ground motion in a magnitude 5, but if we have a magnitude 9 earthquake, it only takes 0.17 G in order to trigger liquefaction. There's lots of combinations of magnitude and distance that can produce a particular peak acceleration. If we look at a ground motion prediction equation, we can plot peak acceleration as a function of magnitude and distance. It's a little bit different way of making these plots, but we can superimpose that earlier set of plots on top of this set of plots and look at the points where the curves intersect, and they define magnitude distance pairs at which we would expect liquefaction to just be triggered for materials with 5, 15, and 25 blow counts. And if we cross-plot those on axes of magnitude and distance, they give us an idea of where we would expect to see, how far away we'd expect to see liquefaction occurring for a 5 blow count material, a 15 blow count material, and a 25 blow count material in earthquakes of different magnitudes. And when we go up to 9.0, and this is an extrapolation, we're out here at pretty large distances, greater distances than we're normally worried about. Well, people have gone out and collected this kind of data, and Brett Maurer is one of them. And I just remembered that I forgot to introduce our 2 new geotechnical faculty, so I'm going to do that at the end of my talk, or maybe just before the end so you don't walk out. They've collected this kind of data that shows the greatest distance in each earthquake at which liquefaction has been observed. And really the black dots here are the ones that are more relevant for what I'm about to show you, because their distance measure is more appropriate than the distance measure that corresponds to the gray plots. But if we take those plots that we just developed based on this Boulanger and Idris' most recent liquefaction procedures, extrapolating out to that magnitude 9, we get a remarkable agreement between the 5 blow count curve, which is about as loose as we typically see these soils, and the empirical evidence, which suggests that at least for these very loose materials, extrapolating our current procedures seems to do a pretty good job. And so we're seeing that it's consistent with our field evidence. Denser soils can liquefy in these bigger earthquakes because we have more shaking. We have in our current liquefaction databases, this is the Chetin et al. Database and Boulanger and Idris. We don't have much data above magnitude 8 or so. There's really very little data, case history data. We'll have more data now with some of the bigger earthquakes that have occurred. Our case history databases really are pretty poor right now. The procedures that people have developed liquefaction procedures from are missing a lot of the earthquakes that have occurred over the last 20 years or so. They haven't been updated. So there's a project that is getting underway by peers called the Next Generation Liquefaction Project. It was conceived of by John Stewart at UCLA, and he and I are putting this thing together to develop a big community database of all case histories of liquefaction. We've been working with Japanese and New Zealanders, more recently with Chileans, to build this big database. It will be available to everybody, and there will be a phase of database building, and then there will be a phase of model building that will be very similar to the NGA project that was conducted for ground motion prediction equations. And so this, over the next 5 to 6 years, I think is going to really revolutionize the way we do liquefaction analyses, both for triggering and for effects. And so a lot of these controversies that we've had, I think, are going to be solved by that project. Drainage is important. We're looking at long duration ground motions here. The ground's going to be shaking for minutes. We normally assume that liquefaction occurs as an undrained process, that there's no chance for drainage to occur. But if the ground's shaking for minutes, then there is that possibility, and that can have an effect on motions. We can see this in numerical analyses. Here we're looking at a relatively thin layer that has drained boundaries. The colors represent pore pressure ratios, so the deepest red is a pore pressure ratio of 1, indicating liquefaction. The blue indicates no pore pressure at all. And if we run our analysis with a permeability of 10 to the minus 4 centimeters per second, we get results that look like this. If we change the permeability to 10 to the minus 3, it looks like this. So in a very long duration motion, we can have dissipation of pore pressure occurring, and that has an effect on the ground motions. Our ground motions at the end of the lower permeability case are pretty weak, and they're much stronger in this case. So for these motions, we may have to pay more attention to drainage effects. If we look at what's going on here, we start out with high effective stresses, then our effective stresses become low, and then they become high again. So we expect our stiffness starts out high, it becomes low, and then it becomes high again. Do we see this thing ever happening? Yeah, we have seen it, and we can detect it now with these time frequency analyses. So this is Onahama in Japan during the Tohoku earthquake. We can see we're starting out here in the early part of this record. The shaking is weak. We don't have much pore pressure, so we have a relatively high fundamental frequency. The second mode is coming in here, and then liquefaction occurs, and our high frequencies drop out. The fundamental frequency drops way down, but then it starts coming back. And it starts coming back because this was a relatively thin layer, and we then get these second modes coming back in, and it stiffens itself back up again. Can we model this? Well, with sophisticated models, we can. Mike Greenfield used the FLIP program with a kind of a different site condition and a different motion, but we see the same sort of thing. We start out high, it liquefies, the frequency goes down because the soil softens, but then pore pressure dissipation occurs, and we see this stiffness coming back. This probably is more important from the standpoint of permanent deformations. If we look at a site with this kind of a profile, relatively thin layer of liquefiable soil, we tilt it a little bit to look at lateral spreading condition, and then we run our analyses, assuming different permeabilities. Then we see that we get differences in the amount of permanent displacement depending on the permeability of that liquefiable soil. And so with a low permeability, it stays undrained, and we get relatively large permanent deformations. If we have a higher permeability, we're effectively drained. We can't build up or maintain much pore pressure, and our permanent displacements are much smaller. And so this means we're going to have to pay more attention to things like permeability and drainage and the coupling of pore pressures and the diffusion equation and the wave equation when we do these types of analyses. So what do we know about liquefiable soil profiles now? We've said that before the liquefaction is triggered, we've got a relatively stiff profile. It can amplify high frequencies, and our strains are generally small. After liquefaction has been triggered, pore pressure has increased. The soil is generally much softer. It can't transmit high frequencies up to the surface. The profile is going to be responding now to lower frequencies, and the strains become much larger. We really have two different soil deposits. We have a pre-triggering soil deposit and a post-triggering soil deposit, and have very different characteristics. What we do now is we use peak acceleration and magnitude to characterize the ground motions for triggering purposes. And that makes sense because those are high frequency parameters. They're describing the higher frequencies in our ground motion. And so the triggering occurs when the soil is still stiff, so we're pretty good there. Most of our procedures now for post-triggering, for the effects of liquefaction, use the factor of safety or some other function of peak acceleration and magnitude. And that doesn't make much sense because the soil is much softer afterwards, and it's not going to respond. Its response is not going to be well correlated to high frequency parameters. Here's a ground motion in the Chiba recorded in Chiba on the east side of Tokyo Bay in the Tohoku earthquake. It's part of the motion. It's up to the time liquefaction occurred at 121 seconds. The peak acceleration, about 0.16 g at that point, and the maximum displacement about 8 centimeters. So some displacement, not a huge displacement. Here's the rest of the record after liquefaction was triggered. If we go out here, we've got 0.03 g peak acceleration or acceleration amplitudes, but we've got 14 centimeters of displacement. So if we divide our 8 centimeters by the 0.16 g beforehand, where it takes for 1 g, we get about 50 centimeters of displacement. After liquefaction has been triggered, 467 centimeters per g of input acceleration. So we see a much greater deformations, even though the acceleration levels are lower because the frequency contents change. The wildlife site, similar type of thing. Liquefaction occurs before that, 0.19 g and only 0.04 centimeters. After liquefaction has been triggered, our ground motions are weaker, the acceleration amplitudes are lower, but we get a lot more displacements, and so the ratio is a big number again. It changes a lot. If we look at what's happening after liquefaction has been triggered, here we've got, in the 50 seconds of shaking, about 13 cycles, 3.8 seconds per cycle. It's a slow motion that's occurring here. If we look at this video, take a look at the gap here between the concrete and the bricks. And I've got about 18 seconds here, and you can see that that gap opens and then it closes, and then it opens and it closes. And there's almost 3 cycles of motion, a little less than 3 cycles of motion during that 18 seconds. So about a 6-second period. So if that had been on sloping ground, we would have seen it open and then not quite close. Then it would have opened up even more and closed less, and we would have seen a permanent deformation occurring. But it would have been on something like a 6-second period. But we're still using things like peak acceleration to try to predict those kinds of deformations. So we've developed a framework to try to improve our ability to predict the effects of liquefaction. And we base it on evolutionary intensity measures that build up with time, so we bring that timing aspect into it. It distinguishes between pre-triggering and post-triggering characteristics of emotions. Now we use the entire ground motion to predict what the effects of liquefaction are going to be, but we know that the effects don't occur until liquefaction is triggered. So why should we be using information from before triggering to predict what the post-triggering behavior is going to be? We don't have to do that if we make use of timing. We can use different intensity measures, different descriptions of the ground motion for the pre-triggering portion and the post-triggering portion. And we'll see that we should be doing that. And we're going to predict our effects just based on the part of the motion that affects those effects, that is the post-triggering part. So we have this conceptual framework, and it kind of looks like this. It's a convenient thing to show graphically. Here's kind of a typical situation that we have with a triggering curve. Let's say we use standard penetration resistance as our measure of the characteristics of the soil, and we'll have some intensity measure. This could be our magnitude-corrected peak acceleration. It could be Aere's intensity, cumulative absolute velocity. It could be a whole bunch of different things, but something that really correlates well to the generation of pore water pressure. So we have a soil with a given density. Liquefaction will be triggered when our intensity measure reaches that curve, that particular value. If that is a evolutionary intensity measure, we can determine then what time we reach that value. So we have the time of liquefaction. And we can divide our loading into the pre-triggering portion and the post-triggering portion. And since the deformations don't develop until liquefaction has been triggered, it's this part that's really going to drive the deformations that occur. So we can take this time history, or this history of this intensity measure, and flip it upside down. Whereas we're seeing how things are generated here, we see how much loading is remaining at a given time here. So we have a ground motion, generated ground motion intensity, and a remaining ground motion intensity. This one doesn't have to be the same one that we used up here, and it shouldn't be the same one that we used up here. The triggering is a high-frequency problem. The effects, the deformations, are a low-frequency problem. So we should be using something it depends on high frequencies for the first part and lower frequencies for the second. Well, if we have this post-triggering intensity measure and we have the density of the soil, we can use numerical analyses or empirical procedures and develop relationships between the density of the soil, the post-triggering loading, and the deformations that would develop. And our deformations would increase as we come up to this in this direction. So high frequency parameter for triggering, low frequency parameter for deformations. If we have, say, a relatively loose soil with a low penetration resistance, it's going to liquefy at a relatively low level of this triggering intensity measure, which means liquefaction is going to occur early in the record, which means that we're going to have a large remaining level of loading, and that combination of a high level of remaining loading and the low density gives us a large permanent displacement. If we have a denser soil, it's going to require a greater level of loading in order for liquefaction to be triggered, which means liquefaction would occur later, which means that there's less remaining loading, and that combination of a low level of remaining loading and the higher density means we're going to have a smaller displacement. And so we're getting a couple benefits here. One is we're just using the remaining loading. If liquefaction occurs late and the soil's not going to be in a liquefied state for very long, then we shouldn't be using the entire level of loading in order to predict deformations. We should just use what remains. We're also allowing ourselves now to use a different intensity measure, something that's more sensitive to the lower frequency components of the ground motion that are really going to be driving those deformations. So we wanted to check this, and we checked it first numerically. We developed a series of profiles of different soil density. We took 80 motions ranging from weak to strong, ran them through. Mike Greenfield did this work, calculated permanent displacements using the flip code, a very powerful Japanese finite element program. We had 800 different analyses. We fit relationships to the triggering and to the displacement that were functions of the blow counts and different intensity measures. What we found was that the magnitude corrected peak acceleration gave us the best fit for triggering, and Arius intensity gave us the best fit to the displacements. So we looked first at a case where we assumed that we had no uncertainty in the penetration resistance, so N160 of 10, and no uncertainty in the PGA sub M value. We then took 30 spectrum-compatible motions. So these motions have the same amplitudes and the same frequency contents, at least as we normally characterize them by means of response spectra. But they were different motions, so they evolved differently in time. And even though they were spectrum-compatible, they came from different peak accelerations, different magnitudes, so they had some different final values here. And liquefaction triggered at this value of the intensity measure, but at different times. When we then plotted the remaining Arius intensity as a function of time, we can bring all of these points down, and they hit at the locations that are indicated here. They had a pretty wide range of Arius intensity, final Arius intensity values. We can make some interesting plots of ground motions this way and look at some interesting characteristics. Here, we're looking at the remaining Arius intensity as a function of the generated magnitude-corrected peak acceleration, so we're plotting points at the same time. So early in the record, the remaining part is high, the generated part is low, and when we get late in the record, the generated part is high, the remaining part is low. We're studying these kinds of characteristics of different pairs of intensity measures. We can normalize them, so we start out by normalizing by the final value of the remaining and the final value of the generated, and we find that they have a characteristic shape here. And we can characterize uncertainty, the distribution in these things, and plot a mean and a 84th and 16th percentile values, and they look kind of like this. We've done some preliminary investigations that show that the shape of this relationship is pretty insensitive to magnitude, distance, site conditions, and basin effects. And so there seems to be a pretty robust relationship here that's going to help us use this information to make better predictions of what the ground motion intensity measures are going to be. If we go back and bring all these points horizontally across, we end up with displacement values that range from about 0.3 to 0.9 meters and we have a standard deviation on the logarithm of the displacement that's 0.23. If we had used the entire ground motion rather than just the post-triggering portion, we would have we'd have an uncertainty value of 0.31. By using the post-triggering portion, we get that reduced down to 0.23. So we get a reduction of uncertainty when we make our predictions this way. And in the coming world of performance-based earthquake engineering, which is going to be probabilistically based, that makes a pretty big difference. That's significant. We did the same thing for settlement problems. There we found that cumulative absolute velocity was a better intensity measure. When we use the entire ground motion, our standard deviation now, it's not logarithmic, 1.5 centimeters, goes down to 1.2 centimeters. A significant difference that, again, in a probabilistic framework is going to be significant. If we consider uncertainty in the blow counts and the cyclic resistance ratio, instead of having a single point here, we've got kind of a cloud of points, but we can go through the same process, work our way around, and we end up with displacements that have a broader range and a higher uncertainty than we had previously. But if we compare what we have using the post-triggering portion compared to using the entire ground motion as we currently do, we're cutting our uncertainty down from 0.8 down to 0.45 or so. And that's a huge difference. And that, in a probabilistic framework, that really will make a big difference. We cut down the probability, say, of exceeding a meter of displacement by a factor of about 5. So it is a promising procedure that we are developing and will continue to develop through this next generation liquefaction project. To conclude, to summarize, this is when my family said they would wake up when they heard those words. Time is an important part of the liquefaction process. Pore pressures build up over time. Deformations develop over time. Time matters. If we know when liquefaction occurs, whether it's early or late in the record, we can make better predictions of the effects of liquefaction. Now we ignore that. So we don't need to do that anymore, and we should be developing procedures that account for timing, in my view. These evolutionary intensity measures can help us account for duration, so we don't necessarily need things like magnitude scaling factors, and they help us bring time into the equation. Our current cycle counting schemes may overpredict the effects of some of the later cycles that are shielded by higher peak accelerations that occur or higher shear stresses that occur earlier in a record. So we have some opportunities to improve things there. Soil stiffness changes and can change dramatically when liquefaction is triggered. And essentially we have two different soil profiles, a pre-triggering profile and a post-triggering profile. They have different characteristics and they respond to different components of ground motions. We know that in the lab, we see it in the field, we see it in model tests in the centrifuge and other places, that our deformations are small before triggering occurs, and then they become large. But they can become large after liquefaction has been triggered. So our higher frequency intensity measures, things like peak acceleration, are great for evaluating triggering, but we can do better in predicting the effects by looking at low frequency ground motion parameters. These timing issues, I think, are going to be particularly important for long duration ground motions like we're subject to here from the Cascadia subduction zone, because the soil is going to be in a liquefied state for a long time. Usually liquefaction, maybe the soil liquefies and you get 10 or 15 seconds of loading while it's in that liquefied state. We may be getting minutes of shaking when the soil's in a liquefied state in a major Cascadia subduction zone type of earthquake. We have a real opportunity to improve our ability to predict liquefaction empirically and analytically with some research efforts that are going on now. The PEER NGL project, I really believe, is going to be a tremendous help to us in the next 5 to 6 years or so in improving our procedures to evaluate both the triggering of liquefaction and the effects of liquefaction. And so before I finish, I'll go back and think back 33 and a half years when I got here. I was one of 2 geotechnical faculty members here at the University of Washington. My understanding is that there were 3 professional engineers practicing in this area who had graduate degrees from University of Washington. Companies were hiring from Illinois and Texas and Berkeley and MIT and that sort of thing. it's been gratifying to see how things have changed over the years, to look out and see so many students that have made my career so rewarding. And it's gratifying to know that we finally got permission to search for another faculty member last year, and we managed to arrange that so that we ended up hiring two, and they're both here. Guys, stand up. Brett Maurer in the light-colored sweater is from Virginia Tech. He got his PhD. He's done a lot of work in New Zealand. He's an earthquake engineering expert. Finally, we have somebody who knows something about earthquakes here in our group. And Mike Gomez is from UC Davis. This is Mike's first day on the job. He just moved into his office today. I remember that day for me. I hope yours was better than mine. And Mike does work in biogeotechnical engineering, and so doing some really interesting things in soil improvement with biological techniques. And he'll be speaking to the seminar, the ASCE seminar in the spring. So great to have these guys on board, and I hope the community gives him the same kind of support that it's given me over these last 33 and a half years. So thank you very much for your attention.
Anybody? Lights here so we can see them.
Okay. Yeah, lights.
Oops.
Yes.
How long have you studied the effects of how long it takes the liquefied state to resolve itself? Does it affect the post or aftershocks?
Well, there are many cases where liquefaction has occurred. The pore pressures can remain elevated for a considerable period of time. Depends on how thick the liquefiable soil layer is. It depends on the boundary conditions, whether they're what the drainage capabilities are. But a soil can remain in a high pore pressure state for hours. And there are lots of cases where soils have liquefied, the pore pressures have dissipated, aftershocks have re-liquefied them. There are a number of cases from the Tohoku earthquake. It's kind of the data we have from Tohoku, at least in the near source region, because the tsunami came in and undoubtedly liquefaction occurred, but the tsunami came in and washed all the evidence away. And so I was there about 10 days after the earthquake, and you could walk around, you couldn't see any evidence of liquefaction. But then some aftershocks came, and all of a sudden there were sand boils. So soils can re-liquefy. There's lots of evidence of that. Did I answer your question? Is that what you asked?
Because what does an aftershock, will it be much easier to trigger the liquefied state, and then the deformations might be greater in that sense, even more so than the initial earthquake?
That's a difficult thing to say. The question was, if liquefaction occurs, is it easier afterwards for aftershocks to cause more damage? Generally, when the soil will liquefy, what we'll see is that the lower half of the liquefiable soil will become denser. Pore pressures dissipate usually by migrating upward, and they often loosen the upper portion of the liquefied layer. And so for the next earthquake that comes along, even if it's an aftershock, that upper portion may liquefy pretty easily, but it's thinner, and typically we don't see as much deformation occurring in aftershocks. Generally, aftershocks are smaller than the main shocks, but for these very large earthquakes, aftershocks can be pretty big. I experienced several 7+s while I was in Japan after the Tohoku earthquake. Small compared to the magnitude 9 main shock, but big enough to get your attention. Dan?
Steve, very interesting methodology you present here. It would have been nice if you had it done before I retired, but my question is, you had a lot of variables obviously with this, a lot of effects of all these parameters. Do you have an overall statement whether this new method is going to have a more conservative or less prediction of deformation that we're using now, or more? Is it just so many factors that you can't make a statement like that?
I don't know that it's going to be less or more for specific conditions. I know it's going to be more accurate, okay? And it'll be less uncertain. And so that uncertainty in this kind of probabilistic performance-based framework, uncertainty drives deformations, or it drives in the ground motions. If you're looking at a spectrum with a peak acceleration, part of that peak acceleration is driven by uncertainty in the probabilistic seismic hazard analysis project. If we can reduce that uncertainty, we can reduce the peak acceleration at 475 years or 2475 or something like that. When we go into these performance-based frameworks for predicting, say, lateral spreading displacement, some of that is going to be associated with uncertainty. And if we can reduce that uncertainty, we can reduce the amount of displacement that we're predicting. And so there's some
cases will be higher, some cases will be lower, but it'll be more accurate.
The mean or the median may be higher or lower, but when you reduce that uncertainty and put it into this kind of a framework, then your predicted displacements will typically be lower, to put it in the simplest terms I can, for a given return period. Yes?
In the world of bridge engineering, we have to design for plastic hinging in the columns, and that typically is going to occur prior to liquefaction occurring, but then once the liquefaction does occur, you've got a completely different state
Yep.
to analyze.
Yep.
How do you see this impacting that analysis or that design, now that we know when that liquefaction, better understand when that's going to occur, and how do we analyze that bridge once that liquefaction occurs and the plastic hinge is still likely to be there?
Yeah. Well, I think there's a great potential for having this kind of timing information to improve soil structure analysis of soil structure interaction in liquefiable soils, because we start out with a stiff deposit and it's an inertial interaction problem that's really important. And so shallow depths, you may get hinging during that time. Then the soil liquefies, and now the soil is moving, and it's going to impose kind of kinematic loading on the piers or whatever is protruding down through the soil. And then it's really kind of a different problem. And now we don't have very good procedures for doing that. I see people saying, well, I'm going to assume that the soil doesn't liquefy and run my response analysis. Then I'm going to assume that it starts out liquefied and run the same analysis through, and I'm going to envelope the responses that I get and take that as being conservative. And it probably is conservative. I don't know that it's always conservative, but I suspect in a lot of cases it's really conservative, and people are having to over-design because of that. So I think that knowing the timing will allow us to address that problem in a much better way. I think there's going to be a fair amount of research work that's involved to do that. It's something I'm interested in, but I don't know if I'm going to get to that before my time at the university is up. But maybe Brett will figure that out and do it better.
Others? I have one last question for you. So you showed the one graph of all the earthquakes in the 60s that led up to a lot of knowledge and new information, and now this new recent trend of large earthquakes. Have we learned all we can from those, or do you think there's a whole new way of things coming?
Well, I think we'll get a lot of great information out of these. That recent group of 6, but before 1964, we didn't really have very good strong motion instruments, so we didn't know what the shaking was. Now in places like Japan, they have this incredible network of recording instruments. So we have this tremendous database of ground motions from these very large earthquakes. We didn't have that before. We're getting some pretty good ones out of Chile. We've got case history data, so we're in the process of trying to analyze all that and see what it means. And there's a lot of new knowledge coming out of that in site response and liquefaction and a whole host of areas. So it takes time to interpret that kind of data, and there are teams that are working hard in New Zealand and Japan, and a lot of us here are working with groups from those countries to try to work with all that data and try to really sort out what has gone on at individual sites and kind of as a whole, and see what we can learn on kind of a regional basis as well as looking at specific sites. So I think it takes time for that process to occur, and I don't want to say I hope we get more big earthquakes, or I don't want to say that I hope we get an earthquake around here, but I would really love to see one that shakes our new Duwamish vertical array and generates some pore pressures when a train is not going by, because the instruments are right next to train tracks. So I don't want to have to filter out train noise to see what the ground was really doing.
Very good. Thank you, Steve.
Thanks.
Stay up inside here for a second. So my name's Greg Fisher with Shannon and Wilson. I just have a short closing statement. Before I do that, I want to make a couple introductions. So Mike Harney here in the front. Mike, you want to stand up real quick? So Mike leads and organizes and coordinates this event every year, and he has a host of Shannon and Wilson people that help him, and I don't want to start naming names or I'll just forget some. But anyway, it's a lot of work between Shannon and Wilson and Mike and the University of Washington, so I think we ought to give them a round of applause too. And next, Steve alluded to it, but his wife Diane and their children Katie and Megan are up there in the back, on purpose probably, but anyway, if you could just wave back there for us. And we heard from Gerard how book smart Steve is, but if he's street smart, he'll say he owes all his accomplishments to them.
All of my accomplishments to them.
So let me just say, I had my whole presentation prepared. And number one, this is an easy close for me because I've known Steve a long time. He was on my PhD committee in the early 90s. So not only is he a colleague and advisor, but also a friend. It's a privilege to be up here with him. But I had this whole presentation prepared to say that how in the old days Shannon and Wilson, tried to find the physical link between the lecturer and Stan, and how with time passes that gets harder. And then he threw the whole motorcycle story in there. So it kind of screwed me up. Now I'm worried we're going to get all these calls from former grad students around the country saying that they picked Stan up from the airport too. We're going to have all sorts of applications for presentations. But in all truthfulness, what we try to do now is find somebody who more embodies the spirit of Stan, who embodies the spirit of ingenuity, of creativity, of intellectual passion and desire and technical excellence. And I know we've succeeded here today with Steve for all his work he's done at the university and, of course, abroad in the field of seismic engineering. It's a great honor and privilege for him to be given this lecture this year. We also, of course, over the years have tried to find speakers who can excite and generate excitement in an audience, and as based on the turnout here, I know we've accomplished that. So I do have a plaque here for Steve. It says, in grateful appreciation to Stephen L. Kramer for the 2017 Stanley D. Wilson Memorial Lecture. Steve, I know you'll appreciate that for a long, long time. And I also have an honorarium here that I hope you'll give to Diane so she can appreciate it for a very, very short time. We do have a celebration downstairs on the first floor to have some food and drink and fellowship, hopefully to reconnect with some old colleagues and friends, meet some new faculty from the University of Washington, and also just to maybe ask Steve some more questions about his research. In closing, I just want to say thank you for coming today. Thank you for being an attentive audience. But mostly, thank you for coming out and helping us support and remember the legacy of Stanley D. Wilson. Please drive safely and have a great evening. All I do is get a picture of it.